Thanks for the introduction. I'm really excited to be here today. My name is Hannah Lee. I'm a fourth-year PhD student at Stanford, and today I'm going to be talking about experimental design in two-sided platforms and specifically the biases that arise. And this is joint work with my advisors, Ramesh, Johari, and Gabriel, Weintraub. So platforms all around us use experiments all the time to test the effect of a new feature before they launch it platform-wide. And the goal here is to see what the effect is of this new feature on a metric that they care about. They want to see that this new feature increases the metric, and then they also want to see by how much it improves it. And then the goal is to estimate the global treatment effect. That is the difference in this metric in a world where everyone sees this new feature versus a world where no one sees this new feature. And for a lot of experiments, the analysis of these experiments is very straightforward. You just randomize people to treatment and control groups, and then you just take the average of the metric in either group, you take the difference, and this gives you an unbiased estimate of the global treatment effect. However, in marketplaces, this is not always the case. It's not always so simple here. And this is because a lot of experiments in marketplaces may violate a classical no interference assumption. This is the assumption that whatever treatment assignment you give to one individual doesn't affect the behavior of another individual. And when this assumption is violated, this can lead to biased estimates. So since we're in a marketplace, people are interacting with each other, people are competing with each other, I think we can imagine how these biases might arise. But let's go through a specific example just to see how this comes through. This example will be really important for getting intuition for why the biases exist, as well as developing intuition for our results later on. Let's consider a toy example. Say we have an online labor platform with one freelancer and two customers. And suppose the online labor platform wants to test this new feature where they show the freelancer's job completion rate. They want to see what impact showing this has on the market. And so they run a customer-side experiment. They randomize the customers into treatment and control. And for the sake of this example, let's say that this treatment makes a customer more likely to book than they would have otherwise if they were a control customer. So then customer A likes this freelancer, customer A gets this treatment, likes the freelancer, and they book them. That means temporarily this freelancer is busy. And now customer B is looking at this marketplace and there's nothing left for them to book. Even if customer B would have booked otherwise, just by making this freelancer more attractive to customer A, you're decreasing the probability customer B will be able to book. Then because of this competition, you'll be underestimating the bookings in global control, overestimating the bookings in global treatment, and this leads to a biased estimate of the global treatment effect. So this example here, I've shown you how there's interference for a customer-side experiment. Since we're on a two-sided marketplace, you could also run an experiment where you're randomizing freelancers, and then something similar will happen there. You'll also have these interference effects. So existing work has shown that the bias caused by this interference can be quite large on these marketplace experiments. And actually the bias can sometimes be as large as the treatment effect itself. However, there's no consensus on just how large it can be, or when it's particularly bad, or what kinds of experiments minimize this bias. And so this is where our work comes in. We develop a theoretical framework that allows us to look at the bias of different types of experiments and compare the performance across different types of experiment designs. We then find that the relative performance of these different designs, of commonly used designs, depends heavily on supply and demand imbalance within the platform. And then there are nice economic intuitions for why this happens. And building on those results, we then propose a more general class of experiment designs that reduces the bias. So I'll jump right into the model. I'll just note that any model that we want to use has to capture the competition effects that we talked about earlier. That's going to allow us to study interference in these experiments. So we model a two-sided platform where customers book listings. This can include platforms where people find book lodging or childcare, tutors, etc. But for the sake of this presentation, we'll keep the ongoing online labor platform model in mind. So here, a listing is a freelancer. Listings can have different types. This could be for example, the experience level or the location of the freelancer. And at every time, a listing can be either available or booked. Now, customers will start to arrive in the platform. They arrive sequentially, and they choose whether or not to book an item. So when they arrive, they see the set of available listings. And then from these available listings, they'll form their consideration set, where they include each item in their consideration set independently with some parameter alpha. And this parameter alpha can depend on both the customer type as well as the listing type. So basically, this alpha is supposed to represent some sort of search and recommendation algorithm on the platform. Now, given their consideration set, they then choose whether or not to book an item from the set using the multinomial logit model. And they have different utilities for listings of different types, as well as a utility for the outside option. And then suppose this customer chooses this item will then become unavailable for a while. Now, notice here that here we have competition between the listings. When the customers are using this multinomial logit model, if one listing becomes more attractive, in comparison, the other listings will become less attractive to that customer. This will be important later on. So now this listing is booked, and then this listing becomes unavailable for some exponential time with parameter tau. What that means is that when later customers arrive, this listing may still be unavailable. And here we have the competition between customers that cause the interference bias that we saw earlier. Then all of the dynamics that we talked about above, they induce a continuous time Markov chain where the state space of this Markov chain is just the number of available listings of each listing type at any time. Now, how do we use this to study experiment design? So to do that, we focus on a class of interventions that changes choice probability, a customer's choice probability. For example, it can change a customer's utility for one of the listings. And then we use this model to study the system dynamics in 3 different worlds. This global treatment world where everyone on the platform sees this intervention, global control where no one sees this intervention, and this experiment world where some subset of the population sees this intervention. The thing that we want to measure, or the thing that we want to estimate, is the global treatment effect, which is just the difference in the rate of bookings between global treatment and global control. Now, one thing to note here is that a platform in reality can only see one of these 3 different worlds at a time. And so what they'll do is they'll run an experiment. They'll be in the experiment world and then try to use these observations to try to estimate what would have happened in global treatment and global control. But since they can't see these actual worlds, they don't know the ground truth, and so they don't know how large the bias is. The nice approach about this modeling the nice thing about this modeling approach is that we can see all 3 worlds. So we know what an estimator would have looked like in an experiment, and we know what the ground truth global treatment effect is. And so we can actually use that to start to study the bias of different estimators and experiment designs. Now, this is a little bit of an aside, but I've told you already that how we want to use this model, but there's still another question where can we actually use this model? Like, is this model actually tractable? And for this initial Markov chain model that we described, the answer is no. It's not very tractable, and it's very difficult to analyze due to all the randomness in customer choice and the randomness in the availability of the listings. So what we do instead is we move to a mean field model where we scale the size of the market. So we scale the number of listings as well as the arrival rate of the customers to infinity. And once we do that, we end up with a continuum model. And this continuum model is it behaves very nicely. It evolves according to a system of ordinary differential equations. We can characterize the trajectory of the system, and we can show that there's a unique steady state, which we can find as a solution to an optimization problem. Furthermore, the use of this mean field limit as a large market approximation is justified. So as we scale n to infinity, as we scale up the size of the market Markov chain does converge uniformly in probability to this ODE solution. And then this is just some of the math formalizing what I've said already. But basically from here on out, all the results I provide are from the mean field model. Okay, so jumping back into the world of experiment designs and platforms, there are two common types of experiments that platforms run. One is the customer side experiment and the other is the listing side experiment. So in a customer side experiment, a customer will come and then they'll be randomized into treatment and control, and depending on their treatment condition, they'll see the market differently. So in our earlier example, a treatment customer would see the previous job histories of all the freelancers on the market, and a control customer would not. A different type of experiment you could run is a listing side experiment. Listings are assigned to treatment or control, and if you're a treatment listing, then you have like the job history attached to your profile. Now, when a customer comes in, they'll see a mix of treatment and control listings, a mix of like listings with and without this extra information. For each type of experiment, there's a very natural associated estimator with these that just compares the rate of bookings between the treatment and control groups. And we'll look into the performance of these experiments. This is the first result that we find. So we find that the bias of an estimator depends on market balance. We can see in this plot here, this is the bias of a customer side experiment. And we can see that it's very large when demand is high, but it seems to be decreasing when demand is smaller. And so we prove this as a theorem that the customer side estimate is unbiased in this demand constrained limit. What's happening here is that in a customer side experiment, the interference really arises when customers compete with each other for the available listings. However, when demand is low enough and there's enough supply, the listings will be regenerating quickly enough that there's no more competition between the customers. When one customer books, the listing will be regenerated by the time the next customer comes. And so there's no more bias. And then a natural question there is, well, here, this intuition seems very natural, but what happens in a listing side experiment? Does a similar phenomenon hold up? And the answer there is no, it doesn't. And in fact, we see that the opposite phenomenon shows up, where a listing side experiment is actually unbiased in the supply constraint regime for large supply. For very little supply, sorry. And there's also some very nice economic interpretation of this, but for the sake of time, I'll skip over that for now. Happy to take questions later on though. But what we've seen in these earlier results is that there are benefits to both types of experiments, just in different contexts in the market. And so we really want to be leveraging both the strengths of both of these experiments. And to do that, we define a new type of experiment, which we call two-sided randomization. Here, we randomize customers and listings into treatment or control. And we see that the intervention only applies when both the customer and the listing are in treatment. So basically, if we look at all the customer listing interactions of the market, there's a 2x2 matrix that'll characterize the treatment control behavior. And a treatment customer on the labor market will only see the previous history of a listing if that listing is also in treatment. And of course, this generalizes the earlier one-sided experiments that we've talked about. If we put all customers into treatment, then this becomes a listing side randomization. We're looking at the variation in listing control and treatment. And if we put all listings into treatment, it becomes a customer side experiment. What this allows us to do is interpolate between customer side designs and listing side designs. So we can now say things like, if the demand is relatively high, then listing side experiments are good. And so we can run a two-sided experiment that's closer to a listing side experiment. And in other areas of the market, we can run a two-sided experiment that's closer to a customer side experiment. So we talk about how we do this in the paper. Happy to take questions though. There's also another thing that we can do from the structure. There's something about the structure that allows us to actually observe competition effects between customers and between listings. And then we can use these different effects to debias an estimator. So using these two insights, we come up with a TSR estimator. And then this TSR estimator we show is unbiased in both the supply constraint limits and the demand constraint limits. And then we also see numerically that for many cases in this relatively balanced market, there can be benefits there with respect to bias as well. So everything I've talked about right now has been focused on the bias, but for any platform actually implementing an experiment, of course, that's not the only thing they're going to consider. They're going to consider the bias variance trade-off. For the sake of time, I'm going to breeze through most of this, but basically we find through simulations that this two-sided estimator has similar variance to the one-sided estimators that we've looked at. And so the takeaway here is that two-sided estimators seem to offer reductions in bias without having significant increase in variance. Now, wrapping up, in this work, we developed a theoretical model that allows us to compare the performance of different experiment designs. We then find that the relative performance of common estimators depends on supply and demand imbalance. And there's really clean economic intuitions for why this happens. And then we propose a more general class of two-sided randomization designs that reduces bias in a lot of market conditions. So there's a lot of future work to be done here. We want to collaborate with platforms to actually implement these TSR designs. We think there's opportunity to use these two-sided designs to heuristically debias existing one-sided designs. And then there's just like a much richer class of experiment designs to consider as well. So in our work, we really highlight where this bias arises and why there is interference in these markets. But I think there's a lot of interesting work to be done in taking these insights and translating to practical platform implementation. Thank you.